Okay, so thanks for coming. I'm glad to be in Berkeley because I live in Oakland, so this is great. Great commute for me today. And yeah, so this is what we're going to talk about. So all of these things, so automatic machine learning, H2O, and sort of scalable machine learning, all wrapped up into one. So let me tell you a little bit about H2O first. So how many of you know about the company and the software already? Most people? Okay, so like not everybody, so I'll just say a few things. So it's both the name of the company that I work at, H2O AI, and also the name of the software platform that I'm going to be talking about today. It's called H2O. We've been around for a little while now, so since 2012. And we're headquartered in Mountain View, but we have offices in a bunch of other places all over the world. About half of our staff is remote, so we have people kind of everywhere. And so the platform itself, called H2O, it's open source, and you can use it in R, Python, Scala, Java, and we have a web interface that we call Flow. And I'm going to go into more detail about what it is, but essentially it's like a machine learning platform, originally kind of just meant for big data. So if you can remember back to 2012, like everybody back in those times was talking about big data. Then everybody learned about AI, and now we're talking about AI. So the original goal was to have an open source platform that would really scale to big data sets, because a lot of the open source tools at that time and still now don't really scale to large data sets. So this is the agenda for the talk tonight. So I'm going to talk about the H2O platform in a little bit more detail, and then talk about what is automatic machine learning, or AutoML, and then I'm going to talk about how do we do that inside of the H2O package. And these slides are, if you go to this link here, it'll bring you to a GitHub that's called H2O-Meetups, and we have all of our Meetup slides in there, but this one will be at the very bottom, so just click around and you'll see the last folder in there will have the date and the name of this meetup, and you'll find a PDF in there that has these slides. Okay. All right, so I said a little bit about H2O already, but let me just go over it in a little bit more detail. So when we use the word distributed, that's a little bit vague. So just to be more clear, what we mean by that is that these algorithms can be run in a multi-core situation. So if you just have a laptop, it'll use all of your cores. But we can also do a multi-node cluster. So if you, let's say, rent 5 or 10 instances on Amazon EC2 or on Google Cloud or something like that, you can kind of make your own little distributed computing cluster, and H2O can run on all of those machines together. You shouldn't do that unless you need it. So unless your data is too big to just fit on one machine, you shouldn't just for fun. I mean, unless you just like slowing down your algorithm for fun. It does slow it down a little bit to distribute it across multiple nodes. But in general, like you should prefer to use like a single machine if you can, and if you can't, then that's when you start to go to a multiple number of machines. And H2O will work on all of those platforms. So the algorithms themselves are written in Java, and one of the reasons that we do that is just we wanted to choose a fast compiled language like Java instead of R or Python, which is not as high performance. And the other thing is that in enterprise machine learning space, Java is still quite popular as I guess I shouldn't say enterprise machine learning space, but just enterprise software in general. Like Java is still quite popular as a platform to produce production code. So having this in Java makes it easy to productionize models. However, most data scientists, and that's engineers and data scientists would use H2O. most data scientists like R or Python, so we're not going to force anybody to use Java. So that's why most of the people that use H2O are using it through the R package or the Python package. And now I'm going to take an informal survey. Who is an R person versus a Python person? And you can be also both. How about R? Okay, how about Python? Okay. Was anybody both? Okay. Oh, okay, wow, good. Love to see that. So usually I just ask because maybe at the end we'll do some demos, and usually I try to do the demos in whichever language is more represented in the group. But it's also easy just to show it in both. So I mentioned this part here. So one of the features of H2O is that you can easily deploy models into production as pure Java code. So you write your code in R or Python. That gets sort of translated into Java automatically by H2O, and your models come out as Java code, basically. Or you can save it as a binary object, but that's essentially what you get. And so we were trying to replace the workflow, which is still popular. I won't say popular, is still common now, which is like, let's say you have a team of data scientists and they prototype something in R or Python, and then you have to hand that over to the team of engineers who then rewrite it in C++ or Java into production. And so there's this kind of like disempowerment of the data scientist or something like that. I guess as a data scientist, that's how I see it. Here, there's not that gap. So as the data scientist, you can produce something just by typing R or Python code that can be easily put into production. And you can, of course, you can put R and Python into production, but what we're looking for here is like very, very fast prediction speed, because that's kind of what's important if you're running something in production. Not all the time, but generally that's a nice feature to have, and so we can get that with this pure Java code. And also, if you can remember back to 2012, when the company started, one of the original goals was to create a machine learning platform that would work on Hadoop, because that was a very popular, it still is very popular, but even way back in 2012, it was like the big thing. And then Spark came along, and then that's the big thing. And then, so we actually rewrote H2O at a given point when Spark came out so that it could also work on Spark. So it can work on Hadoop, it can work on Spark, it can work just on your laptop, it can work on a cluster. So it works very seamlessly with like any computational environment that you have. So that's another feature. And then this is just some language that we use like within H2O. So just so you know what these terms mean when you see them elsewhere. But basically we have two things that you should know about. One is something that we call the H2O cluster, and all that is that's just the name of the Java process where all of this is happening. So that means all your data is in this cluster, all your models are in this cluster, all the computations that are happening in the RAM of the cluster. And really, like I said, it's just a Java process. And so when you type in the R code or the Python code, it's just talking to the H2O cluster, and that's where everything's happening. Okay. And then we have something that we call the H2O frame, and that is a data frame. And the only difference between H2O frames and other types of data frames, like an R data frame or a Python pandas data frame, is that these are distributed data frames. So what that means is if you're in the situation where you have a very large training set, let's say 100 gigabytes is your training set, and you maybe rent out, let's say, I don't know, 5 instances on Amazon EC2. Let's say they're, I don't know, 60 gigs each. I don't know, I'm just making up numbers. But so in that situation, what you would have is some of the data would be on one of the instances, or some of the rows, I should say, would be on one of the instances. Some of the rows would be on the second instance, some would be on the third and fourth, and that's how we distribute the data. So the data just lives where it lives, and we don't shuffle that around, the training data, that is. What we do shuffle around is sort of like metadata about the training between the chunks of rows on each node, and that's how we do distributed training. It's very different for each algorithm how we do that and what kind of data we pass around, but essentially that's how we get away with being able to train like 100 gigabyte training set on machines that are smaller than 100 gigs. Let's say they're each 60 gigs or something like that. So anyway, that's how the data frame works. When you're interacting with it in our Python, you don't know that it's distributed and you don't have to think about that at all. It's just, you can put it out of your mind. But just so you're aware, that's what's happening. And yeah, if you're used to working with pandas data frames, like we have basically implemented a subset of all the things that you could do with a pandas data frame. So you don't have to learn a new way of interacting, like how to slice rows, how to merge. Like we pretty much have the same interface. And it is just a subset because pandas has all this other stuff as well. And the same for R, like if it's a data frame, if you know how to subset or combine or do any kind of operations on a data frame in R, that should also work on an H2O frame. So you don't have to learn new ways of interacting. We try to make it more natural. Okay, so now this is just a little summary of like what is in the library itself. So we have, well, a bunch of machine learning algorithms, both supervised and unsupervised. So sort of just all the popular ones that are, important, I guess, enough. I mean, so one of the things you'll notice that's different between H2O and like a scikit-learn is there are more algorithms available in scikit-learn. So what we've done is kind of narrow in on the ones we think are the most important and also the ones that can be written in a distributed fashion so that we can distribute stuff. So there's probably sort of, less popular algorithms that we don't have. We have gradient boosting machine, random forest, GLM, deep neural networks, SVMs. We're getting GAMs soon, generalized additive models. What else? Is there anyone that has an algorithm that they didn't hear that they would like to see in H2O, or ask if it's in there? What? Mars. So, yeah. We might be able to do something like that once we have implemented GAMs, since I think there's some similarities there. We might be able to reuse some code, I'm not sure. But that's a good one. Okay, add that to the list. Anyone else have an algorithm that they regularly use that they would like to see?
Any built-in hierarchical time series? That would be awesome too.
We have a hierarchical GLM, and that's very new. I think it's new in 3.28, which is the version that came out basically last month. So that's pretty new. I think there's a blog post about it. Anyway, so we try to just add stuff that we think is going to be useful, but also can scale. Okay. And one of my favorite algorithms is stacking or stacked ensembles, where you kind of combine different algorithms together. That's also something that we can do. And other things that we do, these are things that we do all automatically. So if you have missing data, we'll fill that in for you if you don't do it yourself. If we need to normalize any of the features, like if you're using a GLM or something, we can do that automatically. And then for any kind of categorical data, we can one-hot encode that automatically if that's a good idea. Or with the tree-based algorithms, we don't actually need to do that based on how we've implemented tree-based algorithms. We basically keep all the categories together and do something called a group split for each of the trees. And yeah, so a lot of this stuff, if you're used to scikit-learn, you have to specify each one of these things every time you want to train a machine learning algorithm. So, we just look at things that we see are sort of repetitive code, and we try to do some of that automatically. The same with other features. So there's something called early stopping in machine learning algorithms. So this is common when you have, using this would be common when you have something that can overfit easily, like a GBM, like a gradient boosting machine. So you keep adding trees to your GBM, and then eventually, it gets better and better and better, and then it starts to overfit, and then it gets worse and worse. And so as a data scientist, you kind of have to go along in that process and like try to measure and figure out when is it starting to get worse, and then cut off the training. So that's, something you can do. It's not that hard to do it. You just plot the validation error against the training error and then cut it off at a certain point. Or we can try to do that automatically. So we try to do that automatically in the H2O algorithms, and you can tweak like the sensitivity of that. So maybe it's stopping a little too early for you or a little too late. You can tweak that. And then everything else that goes along with machine learning, like cross-validation, grid search, random search. I mean, certainly not everything, but these are some sort of workhorses that you have in machine learning that help you train and validate your models. And then once you have the models, we can do things like look at variable importance and look at model metrics and plots and just various stuff like that. All of our algorithms have built-in variable importance. And we try to basically make, this is, we have the same interface for everything, so we like to support everything. Like if we're going to have variable importance in one algorithm, we might as well have it in everything so that you can always expect, like if it's a model, it's H2O model, it will have these metrics and it'll have these features, etc. So that makes it easier to use if you always know what to expect. Okay, so next I'm going to talk about what is automatic machine learning. Okay, so that's another question. How many of you are familiar with like the term AutoML or automatic machine learning? Okay, so maybe like half. And hopefully the rest of you are here to learn about that, so that's good. So there's no definition really of what is AutoML. I think it's a trendy word in the last year or so, so people are using it in all sorts of ways, but this is at least my opinion of like I'm not going to necessarily define what is AutoML, but I'm going to try to define it in a way by talking about the goals and the features of AutoML. So one of the goals maybe could be just training the best model that you can get in the least amount of time. So that could also, when I say time, that can be actual computation time. And it can also mean like how much time from the data scientist writing all the code, looking at the code, validating the code, analyzing the results, etc. So there's kind of two pieces there that we need to optimize both and make them as small as possible. And so that kind of brings us to the next point here. So one thing we'd like to do is kind of reduce the human effort. We're not necessarily trying to make a tool just so that everyone can do machine learning, although that is kind of one of the consequences of having tools that are easier to use. It makes it more accessible to more people. But really, like, this tool can be used by experts and by people that are new to the field. So, and why an expert might want to use this is because it's still, you're writing one line of code instead of all the million lines of code that you typically write in your data science project when you're testing things out and trying a whole bunch of stuff. So, and for an expert, you might use it more as just like a starting point. Maybe you run it once on your data, see what comes out of it, and then maybe you get some other ideas about how to customize that further. You kind of look at the results, see which algorithms are doing well and which hyperparameter values are working out well, and then maybe you can be inspired and like get some more ideas, or maybe you spend more time on feature engineering or something like that. So I think it's a really useful tool for any level of data scientists. I mean, essentially how this came about is that this is what I was doing. I like stacked ensembles, so I would build like massive amounts of models and then stack them all together, and like the code is just like out of control. So just to simplify my own personal life, I would make a little wrapper function around basically what I do, and that's how we got here. So, and really, like, anyone could make their own AutoML. You just take all the code that you normally do and put a function called AutoML and then shove it in there, and then you have your own. So let's all get inspired and create our own AutoML maybe later. So yeah, and also another side effect is, of course, once it's easy to use, then you don't need to be an expert to do machine learning. You don't need to know every single algorithm and how they all work and how to tune all of them and what are all the special hyperparameters and what are all the values and ranges that you should be looking at. Like, this is all stuff that takes like a very long time to get used to, and then it also changes depending on your data set. So you can as an expert get some sense of what might work on certain types of data sets, and then if you have a new one that's kind of like that, then you could guess, okay, maybe like XGBoost with a low learning rate is kind of what I need for this data set, and you can try that out. But that's all stuff that it takes a long time to learn, and I think this tool of I haven't explained actually what it does yet, but basically training a bunch of models I view it as sort of a learning tool as well. So you're kind of sort of having this consultant join you on the project, and they do a bunch of work for you for free, and which is not realistic, but let's just pretend that can happen. So you have this new consultant, they do all this work, and then they give you the results, and then you say, okay, this is good enough, like let's move on to the next thing. Or you say, okay, I've learned something from this, now I'm gonna maybe try something new inside of H2O, or maybe I've learned that I need to do more feature engineering, and maybe I'm gonna pay attention to that. Yeah, so the other thing is that in general, like, we hope that this is gonna actually improve the performance of your models, like the ones that you're creating yourself. That's maybe not always going to be the case. You could probably come up with something that might beat AutoML, but maybe you can't. It just depends on what your skill set is and what your familiarity with the data set is, et cetera. So, but one of the goals is, like, we want people to be training better models overall. So it's nice to have sort of another person, not a person, but like a algorithm helping you out with that. And then another thing that I think is kind of interesting as sort of a side effect of AutoML is that once we have something that's very easy to use, that you could just kind of press a button, then it's really easy to use this in all sorts of different scientific applications, or let's say you're writing a paper, like you're some kind of like neuroscientist team or something, and you're trying this novel thing of applying machine learning to your data set and to see if you can do some sort of prediction. And maybe this is kind of like some novel scientific research. One thing that would be nice to see in those papers is to see people using an AutoML tool, because then you'll have kind of a whole list of everything they tried, and you can see the full results. It's not just, they found in our package random forest and trained a single random forest, and then there's the paper. So you'll see, like, what is the real range of what can be accomplished in this machine learning problem, not just like what one scientist person who may or may not know a lot about machine learning tried on the problem. So I would love to see people using AutoML as like in more of an applied environment to sort of increase reproducibility. So why does that increase reproducibility? Well, one, it's whether or not you hand the problem to this person or that person, like, you're going to get kind of the same result. This person over here might really like random forest. This person likes deep learning. Like, whoever you pick to work on the problem, you're going to get a very, very different result. So I think having everybody just try one tool and then go off and do whatever else, I think that can help with creating baselines and reproducible research. Okay, any questions so far? Okay. All right, so what is automatic machine learning? So here's just a couple categories of really just machine learning in general. So let's kind of break out the different pieces. Once on one side we have data prep, so that could be anything related to getting the data in a tabular format, or creating new features, or deleting features, or re-encoding features in different representations. And then once we have the data kind of in a little bit static place, then we can train a bunch of models. There's lots of ways that we can do that. And then once we have a bunch of models, this is kind of an optional thing, but I think if your goal is to get the best model, which it might not always be your goal, but if it is, then you want to ensemble some models together, and then you'll get better performance. So this is just a little bit more detail. So what kind of things do we do in data preprocessing? So these are some of the things that I already mentioned are included. Like natively in H2O, all H2O algorithms will do any kind of cleanup of missing data, encoding things when you need to, standardizing and normalizing if you need to. I also mentioned these two things, so whether or not you need to do any kind of feature selection or extraction, that might be included in this category. And then this one is actually quite important. If you have categorical data, the way that you encode that data has a huge impact on the performance of the final model. So, this is especially the case when you have a column that has a lot of categories, like let's say over 100 or over 1,000, sometimes 10,000 categories. Like that can totally screw up your machine learning model if you're not dealing with that in advance. So, and if you've never heard of this before, be aware that like when you have a column that's categorical data, you could be, you can just train a machine learning model and see what happens, or you might want to revisit that and like try to see if there's a different way that you can encode this data so that you get better performance, or that your models train faster. So if you have like 1,000 categories and your algorithm has to one-hot encode those, that means it's adding 1,000 columns to your training set, and so that could increase your training time a lot. So it's not just performance-based or like model performance-based, it's also like time, like it'll affect the time of speed of training. So anyway, we won't talk a whole lot about that, but that's just something to be aware of. And then here's a bunch of different ways that we can generate models. So regular grid search or random search. Something called Bayesian hyperparameter optimization is another technique. There's probably about like 5 or 6 other ones that I could list on here that are all kind of variants of these two, or combinations of those two together. And then in the ensemble category, there's lots of different ways that you can create ensembles as well, but the two probably most popular, I would say stacking or stacked ensembles / superlearning. This is all the same thing, different names. This is probably the most popular, but this one a lot of people do as well, which is called ensemble selection. And that's just kind of a more greedy approach to it, whereas this one, you're actually using machine learning to learn what the best combination of the algorithms are. So there's like 2 levels of machine learning happening. And that's why it works so well, because we all know that machine learning works, solves all our problems, so that was kind of a joke. Okay. What?
Question?
Oh yeah, question, sorry.
So can you turn off the data pre-processing features if you want?
So,
Can I say, hey, I don't expect to have to impute anything and I'd like to know about it, so please don't do that without telling me?
yes, but in H2O AutoML, you cannot tweak that yet. But in all the regular H2O algorithms, you can turn on and off different things. So we probably will expose more control over what happens here, but we don't do a lot here yet to begin with, so we haven't found the need to expose it yet, but that will be something that we would probably do as well. Yeah?
Does AutoML have any type of like imputation feature where for missing data, instead of just like defaulting to
The mean or
tree-based models,
Oh.
it'll actually fill in the gaps with something?
Yeah, so in all the well, I shouldn't say in all. So all the non-tree based algorithms in H2O, we will just impute the mean, basically, or the mode if it's categorical. So that's just the simple, cheap way to do it. So if you want to do something more sophisticated, like use like machine learning to impute,
Or whatever it might be.
Yeah, there's lots of different things that you can do. Then you would just have to do that on your H2O frame before and then do it here. But we'll just do kind of like the quick and dirty way of doing it. Okay, so then now I'm just going to give you a link to a blog post. So this is called, well, I'll just read it out. It's tinyurl.com/flavors-of-AutoML. And the reason I'm linking you to this post is because if you want to know more about like all the different types of AutoML, so I mentioned at the beginning of the talk that that's not a very well-defined term, and people are using it in all sorts of ways. And so what this article hopes to do is kind of like demystify like what are the different types of AutoML, and it's kind of all broken down around the type of data that you have. So if you have image data, you'll do this type of AutoML. If you have text data, you might do this type. If you have sort of tabular data, then you'll do the type that we're talking about tonight. So yeah, people use the word differently, and there's different software packages that handle kind of those different cases. So that'll help you understand, like, based on your data, what kind of AutoML should you be doing and what tools are available for that. So, okay, so now that we're just a little bit comfortable with what is AutoML in general, let's talk about how do we do that in the H2O package. So this, yeah, so I'm just noticing like we have a new version 328, so this is slightly out of date, but this is the same slide that we had earlier with highlighted what we have in H2O right now. Most of the stuff is on like the roadmap for H2O AutoML, but today we have this. One thing that we've been working on for quite a while is automatic target encoding of categorical features. And that's something that will happen hopefully in the next version. But essentially what that is it's trying to prevent you from these catastrophic situations where you put in some column that's, let's say it's zip code or something, and there's like 40,000 different levels, and all of a sudden it blows it up into like 40, and like there's an explosion on your computer or something. So when something's supposed to be automatic, we want to make sure we handle those situations in some safe way. So one thing that we can do is we can look for these high cardinality categorical columns and then do something to them to make them more safe or more efficient or produce better models at the end. And so what we would do is do some sort of automatic target encoding is probably, I mean, that's what we're doing, but you can also do what's called label encoding, which essentially just maps everything. If there's 10 categories, it'll map everything from 1 to 10 and just encodes it as a number. It seems weird because, you're losing, or I don't know, I guess you're not necessarily losing information, but I guess you are in a way losing information, but it does tend to work quite reasonably, yeah.
Then when you're using one of those models on new data,
yeah,
is that new data flowing in and getting processed in the same way?
Yeah, so that's the part that we're working on right now, actually, is like once you have, so adding any kind of encoding, so when we add stuff in H2O, we want to make sure we're not just adding it to the algorithm, like we want the whole thing to work. So when you're deploying that into production and you export it in some format that we have, we want to make sure like you're not missing that piece that you just mentioned. So like if you did the target encoding, you want to make sure that that's available in sort of the bundle that we give you at the end. That's the part that we're working on right now to finish, is how to package that together. So when you would have your AutoML models, and let's say we did apply target encoding to all of them or some of them, then what you would be left over with was something that you could just give your original data just how it was, and we know what we did, and so we'll do the encoding again, and then it gives you the result. So that's another thing that like in some libraries it's kind of messy, and like you have to do it yourself, or you have to remember, oh wait, I did this encoding and now I have to apply it over here too, and then you have to like carry that over, and it's like separated code, and it can be a bit messy. So that's why we like to package everything so that you don't have to think about it.
So these other steps that you have highlighted, is that pre-processing pipeline come with
These two?
the output? The imputation
Oh, these?
one, honeycomb?
Yeah, so this is already stored sort of in the model itself. These are, like, the metadata around these things is very small, so we can just put that in the model easily. But with target encoding, you're creating a little bit more data, like you're creating this mapping, and maybe it's not that big, but we're sort of deciding what is the best way to include. Are we going to just shove it in the model with everything else? Really what we've decided to do really is make it a little bit more generic so that we can open the door for other types of encodings in the future. And we're doing this more elaborate engineering solution, but it will be better in the long run for other things that we add. So yeah, anyway. So yeah, then what we do, and I'll explain this a little bit more on the next slide, but we do random grid search. So the reason we have the word grid in here instead of just random search is in H2O, you essentially, when you do random search, you're just randomly sampling from a discrete grid. So that's why we're just calling it random grid search. Whereas some packages, you can just say, I want any value between 0 and 1, and it will randomly select. So it's just, anyway, sort of random search, that's all I'll say. I'm just getting too much in the weeds here. So, and then we tune each model as well to make sure they're not overfitting. And then we do stacking at the end, which you can always turn this off. I'll talk more about how to customize this later, but basically everything you see here, you can kind of like turn on and off if you don't want it. So why did we do this solution? So well, this is one explanation. So these two things work really well together. So the reason that they work well together is because stacking is basically works well when you have a diverse set of models to start with. So one way to get a diverse set of models is to randomly generate models, and then they're quite different from each other. So it's a bit not as powerful when you use like let's say a sequence of models that you trained using Bayesian hyperparameter optimization. Most of the time they're getting closer and closer together and they're more similar to each other. So when you stack that group of models, it's not as powerful because you don't have the diversity. So that's one reason why we would choose random search and stacking versus like Bayesian optimization and stacking. Probably the most optimal solution would be some combination of those two. And that's probably something that we'll change in the future. But this is also quite powerful because random search is something, and grid search in general, is something that can be done in parallel. You can do it all at once. You can train 100 models at once, 1,000 models at once, and then you're just done. Whereas Bayesian hyperparameter optimization is an iterative algorithm where you train one model and you kind of like check on the results, and then that gets fed into something called a surrogate model, and then that will tell you a new set of things to try, and then you do that, and it's this like sequential process. So one thing that's nice about this more brute force approach is that you can just do it all at once. And just recently we have enabled parallel grid searches in H2O. So one thing that I'll say is that when you use H2O, it's all parallelized like as much as possible to begin with, but what we're parallelizing is the model building itself. So we optimize for training a big model in parallel versus training a bunch of little models in parallel. And that just that's sort of like from our roots as sort of a big data machine learning platform. We optimized so that we would do things that are more beneficial for very big data sets. And so that's why we do that. But however, over time, we realized that a lot of people actually have small data. Well, I'm sure we knew this, but you know, a lot of people have smaller or medium-sized data, so it's actually more efficient if you're training a bunch of models at the same time versus a single model spread out over a bunch of CPUs. Because you might just use that, yeah, I'm not going to go into details, but there's just different ways that you can parallelize things. And so now we can actually do both. And so one of the things that we're experimenting now that we have this parallel grid search in H2O, is how to do that automatically in AutoML so that we're training everything in parallel. But it's kind of a tricky thing because it changes depending on your data set and your architect, or like your compute infrastructure. So the way that you optimize, like how do you choose how many models to train in parallel so that they're not sort of overloading the server if you're doing too much at once, so it's kind of this fine game that we play of like, how do we do the most optimized version of that? And that's something that we're thinking about in AutoML. So given the size of your data and like how much RAM you have, how many models could we train at once? And maybe it depends on whether they're tree models or GLMs, or there's all these factors. So yeah, these are things that we think about when we add stuff. So in H2O, we often add a new algorithm or a new feature into the H2O in general, and then the next phase is how do we incorporate that into AutoML? First we get it stable, working, great, so we added target encoding into H2O, and then the next step was then, okay, how do we do this more automatically in the AutoML algorithm? So there's kind of this phased approach to the way that we develop this. So I'll just say one more thing about this. So if you're more like statistically oriented, the way that you can think about this is that the models, ensembles perform well if the models are making uncorrelated errors. That just means like when the model fails, it fails very differently than its neighbor over here. So like whatever data you give it, probably somebody in the ensemble will know what to do with it and make a good prediction. So yeah, anyway, that's why these things work well together, and that's why we chose this approach. And here's just an overview of the algorithm itself, basically. So we do all this basic data preprocessing, and we're adding more complex preprocessing, as I've mentioned. Then we go through all of our favorite algorithms and usually train a random grid from that. So we will have a bunch of H2O GBMs. We also have XGBoost, if you're familiar with that algorithm. That's another thing where we added it to H2O at some point, and then later on we added it into AutoML. And that has actually made a lot of performance upgrades in the AutoML algorithm itself. Just having XGBoost in there now helps a lot. So that's, if you're not familiar with what that is, it's just another version of a GBM that's quite good. And we also have our own GBM that we call H2O GBM. Yeah, deep neural networks, GLMs, etc. And so we, as the sort of designer of this algorithm, we've kind of just made a decision about which hyperparameters are we going to tune and like over what ranges. Because you can't just, say I'm going to tune every single parameter and every single value that's possible. Then we want to like constrain that a little bit. So we're kind of focusing on like the good parts. That's like up for debate. So it depends like what your data set is. So we're just trying to make something that, works generally, but an area for improvement in the future could be looking at your data set and then making some different decisions based on that. Like, oh, you have wide data, let me do like this type of thing. Or your data is like this, so maybe I want more shallow trees here, So we can make that a bit more dynamic based on the data set. But right now we just try to do something general and rely on the randomness of the grid search to kind of find something good. And then once we have a bunch of models, then we'll do two things. As long as you leave the stacked ensembles on, which they're on by default, we'll train one that is with all the models that you've trained. So let's say you ran it for 100 models, then we'd have a 100 model ensemble. But we also are always thinking about how do we productionize these things. So maybe having like a 100 model ensemble is like not the best idea for production, because when you're making a prediction from a 100 model ensemble, you have to first get predictions from all the models inside. And then once you have those predictions, then you feed that to the meta learning algorithm in the stacked ensemble, and then that makes the final prediction. So, based on how much like latency you need in your whatever your application is, maybe that's fine. But if you're really trying to minimize the speed at which you're making a prediction in production, then you could probably get away with using this other one that we call the best of family ensemble, where we just take the best algorithm from each of the groups. So the best GBM, the best deep neural net, the best random forest, the best blah, blah, blah. And then we have this little more lightweight ensemble. I think there are either 6 or 7 models in the best of family ensemble. So that's a much more lightweight one. It's still going to do better than the best non-ensemble model, but it's also small enough where you could probably put it in production and it's going to be fast enough. And then once you're done with your AutoML run, then what you get back is something that we call the leaderboard, and I'll show you a little bit more about that. That allows you to kind of look at all the models that are trained and compare them. And then, of course, these are just regular H2O models, so then we can always easily deploy them in production cases. And this is the AutoML sticker, which are available over there. If you didn't get one when you came in, make sure to pick one up. Yeah, does somebody have a question? Yeah.
In terms of the hyperparameter random search, the sampling distributions used, is that based on the model itself and what somebody's figured is the best sampling distribution, or is it uniform?
Yeah, so it is based on what we think is most useful, and so we just hard code that in. We say, this is the grid, and I was kind of going down a rabbit hole earlier about like the difference between random search and random grid search. So we would, and just the way that H2O was, or the grid search was designed, we actually have a discrete grid and then we sample from that. So if you want to like have more of the values over here versus the ones over here, if this is like 0 and 1, then you would just put more points here, and so when it's randomly sampling, you're going to get more density here. So it's essentially the same thing, but we just do it in a discrete way. Yeah.
With so many models and so many hyperparameter options, how do you prevent overfitting?
So the question is, how do you prevent overfitting if you're doing so much machine learning and trying so many different things? I think it's sort of just the same way that we generally try to prevent overfitting, is just using a good validation scheme with our data. And so we do cross-validation and compare all the models that way, and then you just make a choice based on that. And typically, this is why you can also use a test set. So if you want to score the leaderboard, so by default, the leaderboard will just return cross-validated metrics and it will sort on that. But if you want to provide a test set, you can also score the leaderboard on a test set, and that's maybe a little bit more safe. But yeah, it's just the same inherent issues, and there's always a chance that you're going to be overfitting because maybe your data is not small enough or big enough, or other things like that. But yeah.
Are there variable importance metrics for AutoML?
So there are variable importance metrics for all the models that you'll train in there, and so the one thing where that's not the case is stacked ensembles. We don't have that implemented yet, but that's something that we are working on. So for the stacked ensemble, you can see how the meta learner valued the input. So you can look at the variable importance for the meta learner, which what that tells you is how important was each of the models in the ensemble. So that's kind of interesting to look at. But it won't tell you the original features. So that's just because it didn't exist, so we have to add it. And we also, I'll show you some other things about the leaderboard, since you're asking about variable importance, and maybe there's other ways that we want to compare models, maybe not just based on model performance, maybe other things that are useful, like prediction speed is something that we've added to the leaderboard, because people want to know, okay, this is the best model, but it's like a super deep tree and it takes too long to use this in production, or it's too complex. But then the one right below it, oh look, that one's like super fast and almost as good as this other one. So we try to give people other metrics. We also added training time. So, you know, a lot of times that's important if you're like working at a company where you're training models, like retraining them every day or every hour, or you're like always training. You might care quite a bit about how long it takes to train. So I will show you all that in a minute. Okay, so here's some code. I'm going to talk about the leaderboard more in a minute, but let me just show you like what does this look like in Python. So what we see here, the first couple lines, okay, we're importing H2O, then we're going to import the AutoML function, and the first line of code in any H2O script is H2O.init. That just means initialize the cluster, and the default with no arguments will just start it locally on your laptop or wherever you're running the code. You can connect, you know, there's other arguments like port, IP, cluster size. That's probably the most important one. Like if you need more memory, then you have to change the cluster size. The default might not be enough. So that's just something to note about H2O.init. And then we need some training data. So we'll import like a CSV, or this could be something else, like an HDFS location or an S3 location, or different data types. Doesn't have to be a CSV file. We have a database importer. I think it's a different function than import file, but I can't recall off the top of my head. But essentially, this is like your pandas read CSV function, or in R, your read.csv or read_CSV if you're a tidyverse person. Yeah, so all this does is it's loading this data in parallel, so it's fast, into the H2O cluster, which is in this Java process. And then it's giving you kind of like a pointer to that data. So that train object, that's a thing, an actual thing in your Python, you know, shell or script. But really the data is not in Python. It's just existing in the H2O cluster. But you treat it like it's just a, you know, pandas data frame or whatever. So that's your training data. So this is how we train the model. So we have to first say, how long do we want the AutoML job to run? So we can do two things. One, we can say the time, or the amount of time that we want it to run. So this is 10 minutes. So run it for 10 minutes and stop. Or we can use max_models, where you say the number of models you want it to run. So I want you to run for 20 models or 50 models or 100 models. So it depends, like, what are you looking for? You know, you probably don't know how long it's going to take to train a single model unless you've already done that. So we give you some different options, and you can use them both together too. So if you want to put, you know, restriction, you know, you think you want like 100 models, but you only want it to train for 4 hours and then stop. So you can combine them together as well. It'll stop when it hits the earliest of the two. And then, so that's just setting it up. And so to actually train or start the AutoML job, you just have to tell it what data you want to use. So training frame. So if you've ever seen H2O modeling functions before, this is exactly how you use any kind of like a GBM or random forest. They all have the training frame argument, and then they have a Y and an X. And so this is a little bit different, because if you're used to like scikit-learn, Y and the X, that's the actual data. The way that we do it is that we say, here's the data. Y is the column name that represents Y, and then X is also could be like a list of columns that could be some subset of the columns. So this way it's a little bit easier, because you can just use one single like block of data, and then you can change the X variable if you want to take subsets of the columns. And it's a little bit, you don't have to create a new data frame with like some partial, you know, number of columns and have a bunch of different data frames floating around. So, and X is not there, it just means everything that's not Y we'll consider to be a predictor column. So that's a lot of times when you have machine learning training data, like it might already come in that format. So whatever the column name is, or you can put an index if you just know the index or there's no names. And then once it's done, you have this AML object, and then there's a bunch of little different things inside, but probably the most important one is the leaderboard. So we look at that. And then this is just the same thing in R. So the only difference is we have just a single function in R. Everything goes in there. The Python version is just a little bit more Pythonic. It's a little bit more like scikit-learn, where you establish what your model is, and then you run the .fit or the .train. And then you have your leaderboard again. And then this is just a screenshot of the flow GUI. So this is our GUI. So anytime you're running the H2O cluster on a machine, it's automatically also running a web server that's hosting this. So this is all local on whatever machine you're running. This is not on, there is no H2O cloud that exists. People do get confused about that because they sometimes think like the H2O cluster is like running on some cloud that somehow we just pay for everybody's machine learning, or I don't know what the business model of that would be. But anyway, we're not running these computations. They're happening on your machine or on a machine that you're renting from Amazon or Google or whatever. There's nothing coming back to us. So anyway, we also have this interface. You can swap between the two. So if you started it up from R or Python and then you want to explore later, looking at the models, you can click around here, or you can just do everything inside of here. This is what the AutoML interface looks like. You'll see some more arguments here that are not exposed, or I didn't show you before, but this is kind of, there's some that are also cut off, but select your training frame. We can exclude certain models. So one that's missing from this screenshot is XGBoost. There should be an XGBoost there. Max models, max runtime. We have some early stopping stuff that you can tweak. Number of folds, like just things that you can have control over if you want, but we have defaults for everything. Okay, so this is what a leaderboard looks like. It's basically just a table of numbers. And in the first column, we'll have the ID for each model that's been trained. So that's how we keep track of everything in H2O. Everything has an ID. So datasets have an ID, models have an ID. I think those are the main two objects that we keep track of. So once you know a model ID, then you can just grab the model and then like look inside and see everything, all the hyperparameter values, the data that it was trained on, like et cetera. So just to conserve space, we just put the ID in there. And one thing that we also do, just to make it a bit clear, is these are auto-generated IDs. So when you're using like regular H2O algorithms, you can call it whatever you want. But these are the auto-generated IDs using AutoML. So we'll put the name of the algorithm on there and then some other information, just so you have some idea of what kind of model it is. Like you want to know, like, are the XGBoosts doing well? Are the GBMs just by looking quickly at this? But then if you want to actually see what are the values of the hyperparameters, then you have to, grab the model and look at it in our Python shell. Or if you're using Flow, you can just click on it and it will tell you. So what we see here is model metrics. So here's some model metrics for a binary classification problem. So the default sort metric that we use is AUC, but you can change that. So if we actually have an argument that's called sort metric. And if you change it to log loss, your leaderboard will be sorted by log loss. You can also, this is just a data frame, so you can resort it later. But at the beginning, if you already know I care about log loss or MSE or mean per class error, then you just tell it to do that. And then it just, sorts things. And so what you'll notice here, maybe if you can see any of the numbers, is You've got 2 stacked ensembles at the top, and that's pretty typical, though it doesn't always happen that way. When it doesn't happen, that means that we need to fix basically something in the algorithm. And when we found a number of data sets where it's not winning, so what that means is like probably we need to do a better job on the stacking, or something else might be going wrong. But typically what you'll see is stacked ensembles winning. Usually the all models is winning. Next would be the best of family, and then you'll see some other models. And so this is also quite typical that we see XGBoost kind of at the top. It depends on what kind of data you have, but it's pretty typical to see XGBoost as kind of the winner. And so we have a couple things that are sort of hard-coded in there, and that's where you'll see the like XGBoost _1, and then the one below it says XGBoost _grid1. So these ones are from the random grid. These are things that we've just put in there that we think are useful. And there's a couple other things that we should probably tweak, which is that these hard-coded ones are actually giving them more time. So that's also a reason that you're seeing them at the top more often. But I think we're gonna possibly change that. Yeah, so you see a bunch of GBMs. Those are the H2O GBMs. Then we see something down here. So we have a DRF, that's distributed random forest. XRT means extremely randomized trees, which is like another version of random forest that's more random. And then we have a deep learning model, which did not do well on this data set, or a couple deep learning. And then, there's a random XGBoost down here that's really bad too. But that's just sort of, the random search produces bad models as well as good. And at the very bottom, this is also quite typical, is that the GLM will be the worst. Does that make people sad because they like GLM? I know. They're great and they're very interpretable. They're easy to deploy. There's a lot of good things about GLMs, except for they usually do worse than like all the other machine learning. But yet they are still one of the most commonly used. And yeah.
Do the other like XGBoost, stacked ensembles, does it do like auto weighting for imbalanced datasets?
It does not do auto weighting, but we have a balance classes parameter exposed, so you can turn that on. There's a ticket that's open for that, so it's a good idea. But we haven't done that yet. But basically, yeah, you can, if you're feeling like your data is highly imbalanced, you can use the typical, there's 3 parameters that we have in H2O in all the modeling functions that control balancing. So it's called balance classes, which is a true or false. That's how you turn it on. Then there's, I think it's called max size after balance. It's not called that, but it's something like max. If you click on the balance classes parameter in the H2O user guide, it will reference the other 2 that are related. It just has to do with like how much do you balance it, basically, and then there's another one that has to do with like multi-class problems.
So, are you like sampling for balancing?
Yeah. There's not like a more fancy method happening. We have talked about adding SMOT or something like that, but we have not done that. And then, sorry, you had a question back there?
I know it's a function of how big your data is, but is there a rough idea of how much time you should give an AutoML model time to train to get a really populous leaderboard like this? Because sometimes I've done it with like 15 minutes and
nothing.
Like 5 XGBoosts, and it's like, all right.
Well, it starts with XGBoost, so that's why you saw that. But yeah, I mean, I always like to do like 20 models, like depending on, like regardless of what my data size is. I prefer to use the max models instead of the time. generally when I'm starting out. And then another thing that I'll talk about is you can start an AutoML process and then like restart it. So you don't have to know, okay, I think I want 100 now, like I think that's the right number. And then, maybe you needed 150 and then you have to restart. So you don't have to do that. You can just, let's see if it's on the next, this will be part of the pro tip section, so hold on. I'll explain that on the next slide. Let me just talk about this real quick. So it's basically pretty straightforward to use this tool, but I just want to give you a few tips to make you aware of how you can tweak it a little bit. So for example, the thing that I showed you on the flow interface, it had all the algorithms listed and you can click on and off ones that you don't want. So if you want to get rid of like all the tree-based algorithms for whatever reason, like let's say you have like super, super wide sparse data, you don't want to have trees, you just turn them off using the exclude algos. We also have an include algos because we had exclude and then somebody wanted include, so we added it. And if you already know that like pretty much trees are gonna run the show here, like just get rid of deep learning, get rid of GLM, get rid of whatever, then you can turn those off too. I would say it's always good to just try like a lot of models first to see, because even if you have, like let's say your deep learning models aren't as good, maybe they're still helping the ensemble get better performance than if you didn't have them. You can experiment. Like once you run AutoML, you have all the models, so you could try to like build different ensembles, like what happens if I remove the deep learning model and then compare it to the one with it in there. Oh, maybe it's like a little bit better because it added some diversity, even though it's not very good. So that's hard to know in advance. So, okay, this is going to be the next slide, the pro tip that I mentioned. So I'll just go over this first. So I mentioned that probably the most important argument for you is in the H2O.init is the max mem size. So so it will just default to something like relatively small so that we don't like have bad experiences with people trying to run this on their laptop and it just like, it's too much. So if you have bigger data, you can increase this, and then you might say like, well, what do those numbers like even mean like for my data set? I don't know. So what we recommend in general is if your data set is, let's say, 1 gig on disk, that you have at least like 4 gigs of RAM, and by RAM I mean the size of the H2O cluster. So you want to have like at least like a 3 to 4 times amount of memory as like the size of your training set. And that's just kind of a recommendation for like a single H2O algorithm. So then if you're running like a lot of models, mostly that memory is used for training, but you also have to store the models in that same amount of RAM as well. So if you're going to run like a big AutoML run, then you want to just make sure there's enough basically space to like have all the models that you're, especially if you have trees, which are kind of memory heavy, or like tree-based models like GBMs and random forests. Anyway, like there's no real like intuition about this. It's just basically if it's not working, you don't have enough memory, and make more. Yeah. So, okay, so this is the thing that you asked about, like, well, it was kind of what you asked about, but I was trying to explain a solution. So if you want to just run it for a little bit, let's say you want to just run it for like 10 models and then stop and like see how it's going, you can do that. And if you reuse, there's an argument called project name. So if you just reuse the same project name, it will like append models to your leaderboard instead of starting over. So then you grow your leaderboard. And one thing that you need to do is like if you're using a seed, you just have to change the seed, otherwise it'll just repeat the exact process that you did and you'll have duplicates of everything. So yeah, that's basically just some pro tips here. And this is a little bit about our roadmap. I already mentioned this a few times, the automatic target encoding. And another thing we want to work on is like better support for wide data sets. So doing some kind of feature selection or extraction automatically. H2O has a word-to-vec implementation, which means that you can give it, like if your training data points are text, using word2vec you can just train a model, but right now you would still have to train that word2vec model, which is basically a mapping from text into numbers, and then give that number representation to AutoML. We just want to skip that because we have all the infrastructure to do that. So sometime in the future, you will be able to just train AutoML directly on text, and where we're just training the word2vec mapping and then doing all that together. That's another reason why we're taking more time to do this proper packaging of any kind of transformations that happen at the beginning with the data. I mentioned this as well. We're missing variable importance for stacked ensembles, which would be nice. We've done a lot of benchmarking on the algorithm, and that's actually part of how we design the algorithm, is just massive benchmarking and trying things out and seeing what works. And it's also where we find mostly where we find where it's failing. We found some data set where like totally weird stuff is happening and we have to figure out why and then fix it. So this is very useful for just improving the algorithm itself. And SVM is already in H2O. We, probably not sure yet. We'll add it to AutoML. And then GAMs, generalized additive models, that's something that's being developed right now in H2O. So it'll be, at least another version before we see that. And so one thing that people ask sometimes are like, well, how many of you know about Kaggle? Almost everybody. So if you don't know what Kaggle is, it's a data science competition platform where they give you a data set and like everybody competes and there's teams, and whoever gets the best performance on the data set wins, and then they win money. So it's, people get excited. And so people are like, well, what if we have AutoML? Like, can I just win Kaggle now and get rich, basically? But that's not, we're not really there yet, I could say. So essentially where we are with AutoML is that there was, so they had this conference called Kaggle Days, which was, well, they've had it a number of places, but they had the San Francisco Kaggle Days, like, I don't know, when is that tweet from? April. And as part of the conference, they had a 1 day or like an 8-hour competition where you get the data set, everybody competes, and then at the end of the day, it's over. And in that scenario, AutoML tools like dominated pretty much. It was true that a human did win, but like pretty much everything in the top 10 or whatever was all AutoML tools. So first of all, yes, they did still win. However, you can do pretty well like in a small amount of time. However, if you have like a 2-month Kaggle competition or 3 months, people that are like obsessed with Kaggle will spend like hundreds of hours like doing all sorts of like crazy feature engineering and all this magic, and then yes, they will still beat AutoML, I think. Maybe someday we can get to the point where AutoML tools can replicate exactly that creativity that people have when they compete. So a lot of it has to do with feature engineering, and so that's another basically thing that AutoML tools need to start to be doing, and we don't do a whole lot of it in the H2O AutoML. We do have another tool at H2O called driverless AI, which is our proprietary tool, where that is kind of the focus. It's like automatic feature engineering, and it's also like very different in a lot of other ways. But for the most part, most open source AutoML tools focus on the model tuning itself and not so much the data side of things, because that is the harder part. It's easy to just write a bunch of code and make a bunch of grids and do, and it's not like easy, but it's more straightforward. Whereas, when you get really creative with feature engineering, that's where it can really boost your model. Anyway, so my point is that I think that we're trending in that direction, but you're not going to win Kaggle using any basically AutoML tool that exists right now, at least that I'm aware of. So you're safe for now. And if you want to see, there are other open source tools. So probably the most common or like widely used other open source AutoML tools are AutoSKLearn, which is like Auto Scikit-learn, and one called Tpot, TPOT, which is also built on top of scikit-learn. Those are probably the most popular. And if you want to see benchmark, so one thing that I don't like about benchmarks is when the tool author makes the benchmark and then their tool wins. It's weird how that is, but that seems to be what happens. So what we decided to do is kind of collectively as an AutoML community is like all get together and design a benchmark that we thought is fair so that it's not over optimized for one person's tool. Because I mean, you can just have any kind of benchmark and you can always win if you like pick the right data sets and like do whatever. So, so we had representation from a lot of different AutoML people, and the people that were not on the paper were also consulted, the authors of all the tools. So anyway, this is a link for if you want to read about that. It's also an ongoing thing. So we built this framework as sort of a way to keep checking as progress continues on all these different tools, like how do they compete against each other, but also it's, like I mentioned before, it's a very useful tool just as a developer of an AutoML tool to have this framework to benchmark. Oh, and I just wanted to show you one plot. So, so this is, what do we have here? So this is, it takes me a minute maybe to explain what this graph is, but essentially what it is at this single line, that is sort of our benchmark. So I think that is, we don't have it on there, but basically what we did was we compared all these AutoML tools to a, it's the random forest. I'm trying to see what the pink line is. I think is the, basically like a tuned random forest is what we called like the baseline. And then if you did better, then you see like you're on this side. I mean, hopefully all the AutoML tools do better than just a random forest, but that's not always the case, which is a bit sketchy for everybody involved. But for the most part, like if you see H2O AutoML is this red line here, so you can see it here. It's mostly, so it's not always on the top, but it's mostly near the top. And there isn't like the short of it is that there isn't a huge difference between H2O AutoML, Tpot, and AutoSKLearn. There's really not, like in terms of performance. And we all use very different techniques. So that's kind of interesting. But it all depends on like what is your scenario? Like, are you running it for a long time or a short time? And like, what are the resources? Because things start to basically break down with both of these tools because they're built on scikit-learn, and there is like some, scalability issues basically with scikit-learn as compared to like an H2O. So the techniques, like if everybody has enough memory and enough space to do their thing, the techniques are very similar and we're getting similar results. Where it starts to be different is like if the data sets are big, or if you're running it for a long time, or like you need more compute power and it gets more difficult, then H2O AutoML does tend to do a little bit better because it's just built on more scalable algorithms. So in a way, it's like we get a head start. But it's really hard to, and one of the things I don't want to do is like here's one plot where like looks like we're winning. And no, I want to emphasize that this is all very like, it very much depends on the hardware and the data size. And so you can get very different results under different circumstances. And so you should kind of look for what is your situation. And like if you have small data sets, you should look at the results for small data sets and then make a decision based on that. If you have big data sets, look there. If you're able to run models for a day versus an hour, like look at the results that are relevant to your data set. Okay, so I need to hurry up and finish. So I'm just gonna also recommend, there's a video. So you can have this paper that I mentioned before be read to you by this nice woman, Rachel, who used to work at Kaggle. She no longer works there, but she does this thing or did this thing where she would like read machine learning papers to you in 1 hour. So that's also like a cool resource. And then these are links to the tutorials. So basically that code that I showed you, like just that little amount of code, that's all of AutoML right there. But we do have a little bit more in-depth tutorials. We have regression problems, classification, like if you want to do more and get the code. So that's located here. And then the user guide is there. And I think that's my last slide. So I'll just stop there and ask if there's any questions. Yeah.
The vertical lines on the chart that you showed for comparing the performance of different benchmarks, what are these vertical lines? These are different data sets, or?
Yeah. So it's really like, basically each point is a data set. I should have explained that, but yeah, you're running, I think there's like 30 data sets here in the binary classification, and they were run for 4 hours. I think on like I can't remember exactly if it's an 8-core Amazon EC2 instance. I have to check the paper again to remember what the size of the machine was, but basically we ran everything for like different time periods. We ran them for 1 hour, for 4 hours, for 8 hours, and the results change based on that, but they're fairly consistent. The only thing that we can say conclusively is like this AutoWeka tool really doesn't work that well at all. Sorry, it just doesn't. But it's like crazy things are happening. But this is a very old school tool. Like this is probably actually the first AutoML tool. There was Weka, which is kind of like the grandfather of scikit-learn in Java, and then there's AutoWeka, and it's really the same research group that was developing a lot of these tools. So there's nothing to be ashamed about. It's just it's an older tool. It's not as efficient. So it has a very similar technique as AutoSKLearn. So it's just not doing as well for a lot of reasons, and it's like not so much maintained anymore. So
the result for that study is public?
Yeah. So this was a paper that was accepted at ICML, which is a machine learning conference, and they have an AutoML workshop, basically. Yeah. And any more questions?
So have you done any performance comparisons for hyperparameter tuning methods, the tuning methods?
We haven't personally, but there's lots of papers about that, and a lot of them focus on like random search versus Bayesian optimization, and essentially it just comes down to like what is your hardware? Like if you can fit everything and do them all, do like all your searches or train all your models in parallel, then you're going to be faster and get to the solution quicker than if you had Bayesian optimization. But it really then depends on like the size of your data and your hardware, because probably you could get the results to flip if you change some of these things. So so basically I think given like there was some paper that I read where kind of the heuristic was like if you spend twice as long on random search, you get the same result as Bayesian optimization, but you could then parallelize that so then it could be faster. I don't know exactly like what constraints they fixed, but yeah. So any other questions? Does everybody know how to install H2O? Pip install H2O, cran H2O. Then you're good to go. Let me just tell you that where you can look for documentation. So docs.h2o.ai is where all the documentation is for all the tools. So, you know, we have a number of different pieces of software at this point, but H2O3, that's what H2O is, and we have this user guide here. That's really the best place to learn H2O. There'll be links to tutorials, and then if you click down here, that's the AutoML page, which will explain everything in more detail, and it will give you those same little code snippets that we had earlier in R and Python. And then I think there's a link to the tutorial there, so hopefully it should be all set. Yeah?
One last question. How do you track of all the projects that use H2O, and then maybe compare performance across?
How do we keep track of everybody's who's applied AutoML to a project? I don't know. Like if they tell us, then we know about it, or if they write a paper. Like if you ever write a paper using H2O, tell us, because we have an awesome H2O repo where we list all the stuff. And you can also see how people have used H2O. So GitHub, H2O AI, awesome -H2O. So there's like blog posts, books, papers, blah, blah, blah. Yeah, so we don't know, like unless it's a customer that we're working with and they give us access to their data, like we won't know, or they tell us what the result was. And that's usually how we find out when things are not working, like why didn't this work on, you know, then, so that's useful information. But yeah, there's no way to really keep track because it's just out in the wild. But yeah.
Do you think it's good for a beginner to learn from, you know, like scikit-learn or H2O, rather than like really, you know, get down to the nuts and bolts and really learn algorithms?
I personally do think it's better to learn with this tool because I do think it's good to eventually learn that other stuff, but I think you don't have to learn that first to be efficient at, you have to learn like the framework, like here's what the data looks like, here's what a training set looks like, here's what cross-validation is. And essentially all the models are just some sort of black box function, so it doesn't really matter. Like that's sort of the last thing that you need to learn. Is like, okay, once I've learned everything else, then I can learn more specifically, like what does this particular black box do and how can I tweak it in ways to get better results? And then you get more, you know, sort of good at what you're doing. But I think that just having this like blank slate of like, this is the training data, this is a machine learning model, supervised machine learning model, these are the results, like once you've got that figured out, then you can go deeper into the, yeah. And I think this will help you also see different hyperparameters, what are good to tune, what are some good values. It kind of gives you some, it's like working with an expert that you can just see what they're doing and you learn from them, and then you can start to improve, I think. Anything else before we wrap it up? Okay, all right, thanks for coming.